Hi everyone, my name is Cristiane Garcia and I'm going to present the work that Professor Bazanella and I have done entitled Selection of Informative Intervals in Routine Operating Data for Using Data-Driven Control Design. We are part of the Data-Driven Control Group in Federal University of Rio Grande do Sul in Brazil. Well, that's how I divided the presentation. First, I will present the introduction, where I will describe our motivation and our proposal. Then, I will briefly describe the virtual reference feedback tuning method, and in the second, I will present the criterion that we are using to search for the informative subsets. After that, I will present the results showing the benefits of using the informative data. And at the end of the presentation, I will talk about some conclusions and future work. In the data-driven control framework, the task of adjusting the controller's parameters is carried out without knowing the process model. So, the controller's parameters are estimated directly from a batch of data collected during a specific experiment. This experiment usually requires to apply a sufficiently rich signal as system's input. However, that signal is different from the signal that's usually applied to the system during routine operation. And performing this specific experiment can be a very costly and undesirable task because it can be time-consuming and it can cause economic loss. So, our question is, could we use routine operating data instead? For many industrial processes, routine operating data is commonly stored in a database. Or, if not already available, it's easily collected since the routine is not disrupted. However, this data may be uninformative and it's affected by noise. Because of that, just using this data to tune the controller's parameters using a data-driven technique will often result in inappropriate tuning. So, we arrive to another question. Could we search for the informative subsets? That is, could we search for the part of the signals that has relevant information? In fact, the search for informative subsets is a subject already explored in the system identification framework, as can be seen through these works, for example. However, it's a subject little explored in the data-driven framework. As far as you know, our previous work is the first that addresses this matter. With all that in mind, we can formulate our proposal, that's to extend our previous work where we have adapted two literature criteria to search for informative subsets to be used with the VRFT method. But we have considered the case where the ideal controller may be constructed using the available structure, that is, full-order controllers. In the present work, we are considering a more realistic case, known as the mismatched case, where the available controller structure does not allow for perfect matching between the desired reference model and what's actually achievable, that is, reduced order controllers. This is a very common situation in the industry where the available controller structure is usually a PID structure. In the paper, we also show that only one of the two criteria could be used to the mismatched case. However, in this presentation, I will focus only on the criterion that works. So first, I will introduce the virtual reference feedback tuning method. The VRFT is a non-iterative, data-driven method. That is, the controller's parameters are estimated using data collected from a single experiment. It's based on the reference model paradigm, where we choose a priori the desired closed-loop performance, that is, the reference model, M, and the controller structure, C bar. For the mismatched case, there is a filter defined as presented in this equation, which depends on the reference model. The application of the VRFT method is presented here as a sequence of steps. In the first step, the data is collected during an open or closed loop experiment. The second step is to define the reference model, the controller structure, and the filter for the mismatched case. In the third step, we generate the ideal controller's virtual input-output signals. The last step is to identify the ideal controller's parameters, usually solving a least squares problem. In this figure, it's presented the case of a linearly parameterized controller, and the controller's parameters are estimated by solving this equation. Now I will present briefly the criterion based on the smallest singular value. This criterion was developed for system identification and designed to remove data with little contribution from the input signal. It uses singular value decomposition to extract the singular values of the regressor matrix. As mentioned before, this criterion was adapted to be used with the VRFT method in our previous work, but considering full order controllers. The discarding criterion is given by this equation. So it evaluates the evolution of the first difference of the smallest singular value over time and tests it against a threshold chosen by the designer. Therefore, the regressor vector and the output sample are discarded whenever this inequality holds. The idea is, since the contributions from the input signal dominate over the noise, if the first difference of the smallest singular value is too small, then it must come from the noise, so it's better to remove those samples. However, we have to choose the threshold. Later, I will show you how I choose it by visually analyzing the plot of the first difference of the smallest singular value. The application of the smallest singular value criterion is presented here also as a sequence of steps. The first step is to collect the input-output data. In the second step, we define the reference model, the controller structure, and the filter. Then, in the third step, we calculate the regressor vector and filter the input signal. With this data, at step 4, we generate the output vector and the regressor matrix. Using the regressor matrix, we calculate the first difference of the smallest singular value over time. Step number 6 consists in defining the threshold. And as I said before, one may use the plot of the first difference of the smallest singular value to define this threshold. In this figure, I present one realization of the data used in the case study. In this case, a step occurs at every 1,000 samples. Observe that the larger values for the first difference occur after the input changes, that is, during the transient response of the system. Those are the informative rows of the regressor matrix because their dynamics are not dominated by the noise. The value of the threshold may be chosen in order to keep these rows and the respective samples of the output vector. That's how I choose the threshold for this example, and through the red line it's presented the informative subsets selected. The next step is then discard the uninformative data and build the regressor matrix and the output vector with the informative subsets. The last step consists in estimate the parameters by solving a least squares problem, using this new regressor matrix and output vector. Now I will present our results. In the case study, we have run 300 Monte Carlo simulations. This is the process transfer function used in the simulations, and that's the reference model chosen. The ideal controller is given by this equation. And, as an example, the parameters of a PI controller with fixed structure will be estimated. The process output is affected by white noise filtered by this model. In order to compare the results, we are using the estimated cost function, which is calculated for each realization, and using the parameters estimated with the informative subset selected using the smallest singular value criterion, and using the entire dataset. The input-output data are collected during an open-loop experiment. A sequence of steps is applied as input signal, and the signal-to-noise ratio is approximately 32 dB. This figure presents the input signal and one realization of the output signal. The histograms of the estimated cost function obtained using the entire dataset and the informative subsets are presented in these figures. In the same figures, it's also presented the mean and median values. The results obtained with the informative subsets are approximately 3 times smaller than the ones obtained using the entire dataset. The histograms also indicate an increase in the parameters variance due to the smaller dataset. The frequency responses of the ideal controller and each controller estimated using the entire dataset are presented in this figure. In this case, the responses of the controllers are quite different from the ideal one. Of course, we do not expect a perfect match because we are using a reduced order controller. However, when using the informative subsets, we can see that the magnitude responses are quite closer to the desired one than the previous responses. The same is seen in the phase plots, although the difference is less pronounced. Finally, we present a step response of the system using the controllers estimated using all data and using the informative subsets. This figure also presents the step responses of the average controllers and the ideal response. Observe that the responses obtained with the selected subsets are closer to the ideal one than the ones obtained using all data. From the results presented, it's evident the benefits of selecting the informative subsets. Now I will present some final thoughts. When using data-driven methods, usually it's required to collect data from a specific experiment. In order to avoid this task, a convenient option is to use data gathered during routine operation. However, the naive use of such data may lead to inappropriate tuning. In the present work, we have applied the smallest singular value criterion to identify the informative intervals. The selected subsets were then used with the VRFT method to tune the controller's parameters of reduced order controllers. The results have shown significant improvement in the closed loop performance when compared to the results obtained using all data. As future work, we intend to extend the mathematical formulation of this criterion to deal with closed loop data, and we also intend to explore the extension of such criterion to other data-driven methods. Thank you for your time.